European semiconductor investments. As the calendar turns to January 2026, the European continent finds itself at a precarious juncture in its quest for technological sovereignty. The grand ambition, articulated with fervor in the early 2020s and codified in the 2023 European Chips Act, was to double Europe's share of the global semiconductor market to 20% by the end of the decade. This goal was born from the supply chain traumas of the pandemic and the sharpening geopolitical rivalry between the United States and China. However, the reality of 2026 presents a landscape that has been radically reshaped by macroeconomic gravity, corporate restructuring, and the inherent friction between political aspiration and industrial execution. This comprehensive review offers an exhaustive audit of semiconductor investments in Europe as of early 2026. The collapse of the Magdeburg dream. The definitive industrial narrative of the mid-2020s in Europe is the dissolution of Intel's manufacturing ambitions in Magdeburg, Saxony-Anhalt. To understand the magnitude of this failure, one must first appreciate the scale of the promise. The project, dubbed Silicon Junction, was envisioned as a $30 billion complex that would bring the world's most advanced chip-making technology, Intel's 1.4 nm 14A and 18 nm 18A nodes, to European soil. It was to be the anchor of a new supply chain, creating 3,000 direct high-tech jobs and tens of thousands of indirect positions, fundamentally altering the economic trajectory of East Germany. By late 2025, however, this vision had transitioned from a pause to a definitive cancellation. The official announcement in July 2025 by Intel's leadership marked the end of the single most ambitious industrial policy project in modern German history. The reasons for this collapse are multifaceted, rooting themselves deeply in the internal crisis of the American chipmaker and the external economic environment of Europe. The primary driver of the cancellation was not German bureaucracy or European regulation, but the catastrophic financial health of Intel itself. In 2025, the company reported deep red figures, including a staggering loss of $2.9 billion in a single quarter. This fiscal hemorrhage was the result of a perfect storm of declining market share in the data center sector, where competitors like AMD and Nvidia had seized technological leadership, and a sluggish recovery in the personal computer market. Under the leadership of former CEO Pat Gelsinger, Intel had pursued a strategy of IDM 2.0, an aggressive attempt to regain manufacturing leadership by building massive new capacity in Arizona, Ohio, Ireland, Israel, and Germany simultaneously. This flight-forward strategy required capital expenditures of historic proportions. However, as cash flow dried up, the company faced a binary choice: to retrench to its core operations in the United States or risk insolvency. The new leadership, including Lip-Bu Tan, who joined the board and later communicated the restructuring, viewed the aggressive expansion into high-cost regions like Germany as unwise and excessive. They argued that the projected demand for the Angstrom-era chips simply did not justify the tens of billions in upfront capital required to build the Magdeburg site. Even with the German government's promise of $9.9 billion in state aid, a subsidy package that required months of grueling negotiation with the European Commission, Intel would still have been required to raise approximately $20 billion of its own capital. In the face of mounting losses and a stock price that had shed massive value, this capital mobilization became an impossibility. The cancellation was, in corporate terms, a pulling of the ripcord to save the parent entity. Beyond the financials, there was a profound technological disconnect. The Magdeburg fab was intended to act as a foundry, manufacturing chips for external customers using Intel's unproven 14A and 18A process nodes. This was a radical departure for Intel, which had historically only manufactured its own designs. The success of the Magdeburg plant, therefore, depended entirely on Intel's ability to attract customers like Apple, Qualcomm, or Nvidia to manufacture in Germany. By late 2025, it became clear that these customer commitments were not materializing at the necessary scale. Potential clients remained skeptical of Intel's ability to deliver on its technological roadmaps, having seen repeated delays in previous generations. Furthermore, Intel admitted in late 2025 that it might drop the development of the 14A technology entirely if sufficient customer interest did not emerge. This admission rendered the Magdeburg project technologically redundant before ground was even broken. Building a $30 billion factory for a process node that might never be commercialized was a risk that no board of directors could countenance. The implications for the region of Saxony-Anhalt are severe and long-lasting. The state government had staked its economic planning on the Silicon Junction, investing heavily in infrastructure upgrades, water treatment plants, and educational programs to support the fab. The cancellation leaves a 400-hectare void in the Erlenberg Industrial Park and a significant gap in the state's budgetary planning. The 3,000 promised jobs were not merely construction roles, but high-value engineering positions that were expected to arrest the brain drain of young talent leaving East Germany. With the project's termination, these opportunities have evaporated. Moreover, the cancellation has inflicted psychological damage on the European industrial psyche. It demonstrated the fragility of the national champion model of industrial policy, where billions in public money are pledged to a single foreign corporate entity whose strategic priorities can shift overnight due to factors entirely outside European control. The Magdeburg pause, initially announced in 2023, was widely interpreted by insiders as a soft cancellation, a way to manage political fallout while the company sought an exit. The confirmation in 2025 validated these cynics, proving that the EU Chips Act's reliance on attracting mega-projects from distressed incumbents was a flawed strategy. The subsidies earmarked for Intel are now being rechanneled into a diverse set of technology projects, ranging from quantum sensor metrology to mature node capacity, signaling a shift from whale hunting to ecosystem gardening. The Dresden exception, the success of the cluster model. If Magdeburg represents the failure of the field of dreams approach, build it and they will come, then Dresden represents the triumph of the cluster model. The European Semiconductor Manufacturing Company, ESMC, a joint venture led by TSMC, stands in stark contrast to the Intel debacle. As of January 2026, this project is proceeding precisely on schedule, immune to the turbulence that claimed its counterpart in Saxony-Anhalt. The ESMC project is structured fundamentally differently. It is not a wholly owned subsidiary of a foreign giant, but a joint venture involving TSMC 70%, Bosch 10%, Infineon 10%, and NXP 10%. This ownership structure is the key to its resilience. The minority partners, Bosch, Infineon, and NXP, are also the primary customers for the fab's output. They have guaranteed the offtake of the chips produced, effectively eliminating the customer acquisition risk that doomed Intel's foundry ambitions. The fab is being built to satisfy existing, verified demand from the European automotive and industrial sectors, rather than speculative demand for future smartphone processors. The physical progress of the ESMC facility is tangible proof of its viability. Following a high-profile groundbreaking ceremony in August 2024, attended by European Commission President Ursula von der Leyen, the project moved immediately into the execution phase. Throughout 2025, the site saw the completion of massive earthworks and the laying of foundation slabs. By late 2025, Reports confirmed that the main structural construction phase was nearing completion, with the steel skeletons of the cleanroom buildings rising above the Dresden skyline. The schedule for the future remains firm. The project is set to begin the critical phase of move-in, the installation of highly sensitive manufacturing equipment, in the second half of 2026. This timeline has held steady despite global supply chain fluctuations, a testament to TSMC's legendary project management discipline and the German construction sector's prioritization of the site. Volume production is targeted for late 2027, a date that customers in the German automotive industry are counting on to relieve their dependence on Asian imports. The ESMSC fab does not aim for the headlines of the Angstrom era. It is designed to produce chips using 28-22 nanometer planar CMOS and 16-12 nanometer FinFET process technologies. In the world of consumer electronics, these nodes are considered mature, bordering on legacy. However, in the world of automobiles and industrial robots, they are the cutting edge. These nodes offer the optimal balance of performance, cost, and reliability required for microcontrollers, sensors, and power management ICs. By focusing on these nodes, ESMSC avoids the extreme technical risks and astronomical costs associated with extreme ultraviolet lithography, which is required for sub-7 nanometer manufacturing. The fab is a workhorse facility designed to churn out the 40,000 wafers per month that keep Mercedes-Benz assembly lines running and Siemens factory automation systems functioning. This alignment with the actual industrial base of Europe, rather than the aspirational digital economy, is what makes the project viable. Recognizing that concrete and silicon are useless without skilled labor, TSMC launched a preemptive strike on the talent shortage, the Semiconductor Talent Incubation Program Taiwan, STIPT. This initiative, launched in 2024, has become a model for cross-border workforce development. By late 2025, the program had successfully cycled multiple cohorts of students from Saxon universities, specifically TU Dresden, to Taiwan. These students spent months undergoing rigorous academic training at National Taiwan University, NTU, and National Taiwan University of Science and Technology, NTU-ST, followed by hands-on practical training at TSMC's Newcomer Training Center in Taiwan. The program's success was such that in late 2025, the German Federal Ministry of Education and Research signed an agreement to expand it nationwide, opening spots to students from across Germany, not just Saxony. This ensures that when the ESMSC fab opens its doors in 2027, there will be a cadre of German engineers already indoctrinated in TSMC's operational culture and technical standards. This human capital strategy addresses the trust challenge identified by workforce experts, convincing young apprentices to commit their careers to a factory that doesn't yet exist. By sending them to Taiwan to see the scale and sophistication of TSMC's operations firsthand, the program builds a belief in the future reality of the Dresden project. The French stagnation, STMicroelectronics and GlobalFoundries, Crolles. The Crolles expansion was intended to be the crown jewel of the French semiconductor resurgence. Located in the Silicon Valley of the French Alps, the project brought together STMicroelectronics, Europe's largest chipmaker, and GlobalFoundries, the US-based foundry giant. The vision was to create a megafab capable of producing high-volume, fully depleted silicon-on-insulator wafers, a technology pioneered in nearby Grenoble. By 2026, this vision has largely dissolved, leaving behind a complex industrial and legal challenge. The Crolles joint venture, announced in July 2022, was predicated on a symbiotic need for scale. STMicroelectronics required additional capacity for its STM32 microcontrollers and automotive products, but wished to share the massive capital burden of a modern 300mm fab. GlobalFoundries, seeking to expand its global footprint beyond the US and Singapore, viewed France as an entry point into the European automotive ecosystem. The technological linchpin was FD-SOI. Unlike the FinFET transistors used in high-performance computing, example by Intel or TSMC, FD-SOI offers a unique balance of performance and power efficiency at mature nodes, 18 nanometers to 28 nanometers. It is particularly unparalleled in RF and analog integration, making it ideal for automotive radar, 5G transceivers, and secure IoT devices. The joint fab planned to merge GlobalFoundries' 22FDX process with ST's proprietary roadmap, targeting a capacity of 620,000 wafers per year by 2028. By mid-2025, the project's momentum had arrested. In November 2025, industry reports confirmed that the collaboration had been effectively suspended. The root cause was a divergence in corporate strategy, driven by the global downturn. GlobalFoundries, facing a softening market and shareholder pressure to improve robust profitability, engaged in a strategic retrenchment. With its fabs in Malta, New York, and Singapore running below optimal utilization, the economic rationale for pouring billions into a greenfield expansion in high-cost France evaporated. The company quietly slowed its participation, stating publicly that expansion would align with customer demand, a corporate euphemism for halting investment. This withdrawal was not merely a pause, it was a capital flight back to core assets, leaving STMicroelectronics as the sole tenant of a project designed for two. The suspension exposed the critical fragility of the EU Chips Act's governance. The 2.9 billion euros in French state aid approved by the European Commission was contractually tied to the specific joint venture structure. When GlobalFoundries ceased its capital contributions, the conditions for the aid were no longer met. France found itself in a bureaucratic trap. It could not simply transfer the GlobalFoundries portion of the subsidy to STMicroelectronics to allow it to proceed alone. Doing so would require a new state aid notification to Brussels to prove the incentive effect for a solo project, a process that involves months of analysis, competitor consultation, and legal drafting. As a result, billions of euros in approved funding sat idle in 2025 and early 2026, technically allocated but legally inaccessible. This capital freeze halted the expected economic multipliers for the Greifswald Valley, where local infrastructure projects, housing and transport for the anticipated workforce were left in limbo. Despite the collapse of the partnership, STMicroelectronics has not abandoned the Crolles expansion entirely. Instead, it has pivoted to a Plan B focused on its internal needs. The company is continuing to fit out the facility, but at a reduced cadence and with a modified scope. The Crolles 300mm fab is now being positioned as the core of ST's internal digital products ecosystem, specifically for advanced microcontrollers and future edge AI derivatives. ST is also converting legacy 200mm capacity at the site to support advanced packaging and electrical wafer sorting, activities that do not require the massive scale of the original JV, but add significant value. While the megafab dream is deferred, the site is evolving into a more specialized, albeit smaller, node in ST's network. The failure of the JV has forced ST to align the expansion strictly with its own profitability, decoupling its fate from the volatility of a foundry partner. The Italian fortress, STMicroelectronics, Catania, Sicily. If Crolles represents the fragility of partnership-based expansion, the STMicroelectronics site in Catania, Sicily, represents the resilience of vertical integration. In this brownfield location, nestled in the shadow of Mount Etna, Europe is successfully building a global stronghold for silicon carbide technology. To audit the status of the Catania investment, one must appreciate the material science that drives it. Silicon carbide is a wide bandgap semiconductor. Its electronic bandgap is roughly 3 times that of silicon, which allows SiC devices to operate at much higher voltages, 800 volts plus, and temperatures while switching faster and with fewer losses. This physics is the enabler of the modern electric vehicle. SiC inverters allow cars to charge faster and drive further on the same battery. However, SiC is notoriously difficult to manufacture. The crystals must be grown at temperatures exceeding 2500 degrees Celsius via a process of sublimation, turning solid powder directly into gas and back to solid. This process is slow, energy-intensive, and prone to crystallographic defects that render the chips useless. Furthermore, SiC is the second hardest material on Earth after diamond, making the slicing of crystal boules into wafers a costly and time-consuming bottleneck. Recognizing that the supply of high-quality SiC wafers was the primary constraint on growth, STMicroelectronics embarked on a strategy of total vertical integration. The Catania Silicon Carbide campus was designed to house every step of the process: manufacturing the substrate, the raw wafer, growing the epitaxial layer, the active layer, fabricating the device, and packaging the module. This strategy addresses the margin stacking problem. By producing its own substrates, ST eliminates the margin paid to external suppliers like Wolfspeed or SiCrystal. More importantly, it creates a tight feedback loop between the material scientists growing the crystal and the device engineers making the chip, allowing for rapid iteration and yield improvement. As of early 2026, the Catania project is actively ramping up and meeting its critical milestones. The site has become the spearhead for ST's transition from 150mm 6-inch to 200mm 8-inch wafers. This transition is an economic game changer. A 200mm wafer has nearly 1.8 times the surface area of a 150mm wafer. Because the edge exclusion, wasted area near the rim, is proportionally smaller, the yield of usable chips increases by even more than the surface area suggests. The substrate manufacturing facility, supported by 730 million euros in Italian state aid, part of a broader $2 billion package, is now operational and ramping toward the goal of supplying 40% of ST's internal needs. The fully integrated 200mm volume manufacturing line is scheduled to begin commercial production in Q4 2025, cementing its status as a first-of-a-kind facility in Europe. The success in Catania highlights the effectiveness of state aid when applied to an existing ecosystem. The Italian government's support was swift and targeted. Unlike the complex consortium in France, the aid in Italy was directed at a single national champion, ST, to solve a specific technological hurdle: substrate production. The Etna Valley cluster, with its deep ties to the University of Catania and the National Research Council, CNR, provided a ready-made workforce of specialized engineers, mitigating the talent shortages that plague greenfield sites. By 2026, Catania has effectively become the SiC capital of Europe, a status that is insulated from the broader digital market downturn because the long-term demand for power electronics remains tied to the immutable laws of the energy transition. German retreat, Wolfspeed and ZF, Saarland. The cancellation of the Wolfspeed and ZF project in Saarland, Germany, is arguably the most significant failure of the European Chips Act era. Announced with immense fanfare in 2023 as the world's largest SiC fab, the project's collapse by late 2025 serves as a cautionary tale regarding greenfield risks and the volatility of the U.S. technology sector. The project was envisioned as a €3 billion joint venture to transform the site of a retired coal-fired power plant in Ensdorf into a semiconductor powerhouse. Wolfspeed, the Durham, North Carolina-based leader in SiC technology, planned to hold the majority stake, with German Tier 1 supplier ZF, Friedrichshafen, taking a minority position to secure chip supply for its automotive drivetrain business. However, the project was built on a fragile financial foundation. Wolfspeed, unlike ST or Infineon, was a pure-play SiC company with high capital expenditures and negative free cash flow. Throughout 2024, the company struggled with the ramp-up of its flagship Mohawk Valley fab in New York and faced severe headwinds from the softening EV market. By 2025, Wolfspeed's stock had collapsed, and the company faced a liquidity crisis that forced it into Chapter 11 bankruptcy restructuring. Although Wolfspeed successfully emerged from Chapter 11 in September 2025 with a cleaned-up balance sheet and reduced debt, the restructuring plan necessitated a ruthless focus on capital efficiency. The new Wolfspeed could no longer afford a speculative multi-billion euro capital project in Europe. In October 2025, the company officially announced the discontinuation of development for the Saarland site. Simultaneously, the German partner, ZF, was undergoing its own crisis. The rapid shift away from internal combustion engines had reduced the complexity and value of automotive drivetrains, forcing suppliers to consolidate. Facing a severe downturn in orders, ZF announced plans to cut up to 14,000 jobs in Germany by 2028. In this climate of austerity, maintaining an investment in a delayed, high-risk fab was politically and financially impossible. ZF withdrew its support, effectively ending the project. The failure of Saarland also highlights the specific disadvantages of Germany as a location for new industrial builds. As a greenfield project, the Saarland site required the construction of entirely new infrastructure: clean rooms, water treatment, specialized power substations, from scratch. This front-loaded the capital risk significantly compared to expanding an existing site. Furthermore, Germany's high industrial energy prices were a critical deterrent. SiC manufacturing is extremely energy-intensive due to the high-temperature crystal growth process. Despite discussions of a subsidized bridge price for electricity, the long-term operational expenditure, OPEX, in Germany remained significantly higher in the US, where Wolfspeed could benefit from lower energy costs and the operational tax credits of the Inflation Reduction Act. The German government's inability to guarantee competitive energy costs rendered the business case for a pure-play manufacturer unviable once the cost of capital increased. Onsemi, Rožnov pod Radhoštem, represents the triumph of the brownfield strategy and validates the potential of Central Europe as a high-tech manufacturing hub. Rožnov pod Radhoštem is not a new name in semiconductors. The town was the center of silicon production for the former Czechoslovakia under the state-owned Tesla conglomerate. Onsemi acquired these assets years ago and has steadily upgraded them. When the company looked to expand its silicon carbide capacity in 2024-2025, Rožnov offered a unique proposition: an existing site with established permits, existing utility connections, and, most importantly, a workforce with generational expertise in crystal growth. Unlike the greenfield struggle in Saarland, the Rožnov expansion is a brownfield project, an upgrade and enlargement of an existing footprint. This drastically reduces the permitting time and construction risk. In an industry where time to yield is the critical metric, the ability to leverage existing infrastructure gave Rožnov a decisive advantage over potential greenfield sites elsewhere in Europe. The project, approved for 450 million euros in Czech state aid by the European Commission in late 2025, involves a total investment of 1.64 billion euros. It is designed to be an end-to-end facility, covering the entire production chain from silicon carbide crystal growth to wafer slicing, epitaxy, and device fabrication. This end-to-end capability is rare. Most fabs purchase wafers from third-party vendors. By integrating crystal growth on-site, Onsemi captures the value of the substrate, the most expensive part of the silicon carbide BOM, and insulates itself from supply chain shocks. The European Commission recognized this integration as first of a kind in the region, justifying the state aid. For the Czech Republic, this is the largest single foreign investment in its modern history. It fundamentally shifts the country's position in the automotive value chain. Rather than being an assembly hub for German OEMs, Czechia becomes a primary producer of the critical semiconductor technology that defines the performance of future vehicles. The project is expected to create 3,000 high-value jobs and contribute heavily to the region's GDP. More broadly, it cements the Central European Silicon Cluster, linking Dresden, GlobalFoundries, Infineon, and TSMC with Czechia, Onsemi, as the industrial heart of the continent. While the western edge of this cluster, Saarland, has crumbled, the eastern axis is solidifying, driven by lower labor costs, strong technical education, and effective government support. Pragmatic Semiconductor, Durham, UK. While the global media focuses on the race for the nanometer, trying to squeeze more transistors onto silicon chips for AI and smartphones, Pragmatic has inverted the paradigm. Their technology does not seek to be the fastest or the smallest, it seeks to be the cheapest and the most flexible. Pragmatic specializes in flexible integrated circuits, or FlexICs. Unlike traditional chips, which are etched onto rigid, expensive silicon wafers that take months to process, Pragmatic's chips are printed onto thin, flexible polymer films using metal oxide thin film transistors, or TFTs. This process eliminates the need for the most expensive step in chip making, the silicon substrate itself. The strategic implication of this technology is profound. Silicon chips are economically unviable for low-cost items. One would not put a 50-cent silicon chip on a 10-cent yogurt pot to track its recycling status. However, Pragmatic's FlexICs, costing a fraction of a cent, enable the Internet of Trillions. They allow intelligence to be embedded into fast-moving consumer goods, or FMCG, medical consumables, bandages, blister packs, and logistics labels. This capability is central to the circular economy, a key pillar of UK and EU environmental policy, as it allows waste management systems to digitally identify materials for recycling. As of early 2026, Pragmatic's flagship facility, Pragmatic Park in Durham, is fully operational. The site was officially opened in March 2024 by HRH The Princess Royal, marking a symbolic milestone in the UK's industrial revival. It's the UK's first 300mm semiconductor fabrication line. In the silicon world, shifting from 200mm wafers to 300mm is a capital-intensive upgrade that increases efficiency. For Pragmatic, this format allows them to produce billions of chips per year on a footprint significantly smaller than a traditional fab. The facility is designed to host up to 9 fabrication lines. By 2025, the company had launched its Gen 3 platform, achieving a 10x improvement in digital power efficiency and a 3x reduction in area compared to previous generations. the company secured a record-breaking £162 million Series D investment in late 2023, backed by the UK Infrastructure Bank, now part of the National Wealth Fund, and M&G Catalyst. This remains the largest venture capital round for a European semiconductor company in recent history, validating the government's strategy of backing deep tech scale-ups. The Durham site is not just a factory, it is a prototype for a distributed manufacturing model. Pragmatic's fab-in-a-box concept allows production lines to be installed directly at customer sites. In a traditional model, a supply chain shock in Taiwan halts production globally. In Pragmatic's model, a fab-in-a-box located at a packaging company's warehouse in Manchester or Mexico continues to run independently. This decentralization creates extreme resilience, a core objective of the UK Semiconductor Infrastructure Initiative. By controlling the manufacturing equipment and the process IP, the UK retains leverage. Unlike fabless design firms that rely on TSMC and thus are subject to US export controls or Chinese blockades, Pragmatic owns the entire stack. Vishay Newport Wafer Fab, Newport, UK. The Newport Wafer Fab, NWF, in South Wales has been the protagonist of the most contentious chapter in recent British industrial history. Formerly owned by Nexperia, a Dutch company with a Chinese parent, Wingtech, the facility was the subject of a retroactive investigation under the UK's National Security and Investment Act, NSIA 2021. The UK government concluded in late 2022 that Chinese ownership of the UK's largest semiconductor asset posed an unacceptable risk, not due to the technology NWF possessed at the time, which was mature silicon, but due to the potential for the site to be repurposed for advanced compound semiconductors, a critical dual-use technology. Consequently, Nexperia was ordered to divest the site. In March 2024, US-based Vishay Intertechnology completed the acquisition of NWF for $177 million. This transfer of ownership from a Chinese-linked entity to a US-headquartered NATO ally marked a definitive realignment of the UK's semiconductor assets into the Western security sphere. By 2026, the uncertainty that plagued Newport has been replaced by aggressive expansion. In March 2025, Vishay announced a massive £250 million investment to upgrade the facility. This capital injection is a mix of Vishay's own balance sheet funds and support from the UK government's Automotive Transformation Fund, ATF, highlighting the state's active role in de-risking private capital. The site is undergoing a metamorphosis from a general-purpose silicon foundry to a specialized manufacturer of silicon carbide trench MOSFETs and gallium nitride power devices. As of early 2026, the new epitaxy reactors and high-temperature annealing furnaces required for SiC processing are being installed. The clean room is effectively being rebuilt from the inside out to handle the unique thermal and chemical requirements of compound materials. The Newport Fab is the physical anchor of CS Connected, the world's first dedicated compound semiconductor cluster. This ecosystem, centered in South Wales, includes IQE, which makes the wafers, Cardiff University, research, and various packaging firms. Silicon carbide is the unsung hero of the green transition. Chips made from SiC can operate at higher voltages and temperatures than silicon. When used in an electric vehicle inverter, they reduce energy loss by up to 10%, which translates directly to longer range or smaller, cheaper batteries. By securing SiC production in Newport, the UK ensures that its automotive sector, JLR, Nissan, etc., has a domestic supply of the most critical component for electrification. The visit of Chancellor Rachel Reeves and Technology Secretary Peter Kyle to the site in March 2025 underscored its importance. The fab is proof of the government's industrial strategy in action, saving a strategic asset from hostile ownership and pivoting it towards high-growth green industries. Infineon's expansion in Dresden is the single largest investment in the company's history, valued at €5 billion. This project, known as Module 4, or the Smart Power Fab, is a concrete manifestation of the EU CHIPS Act's Pillar 2, Security of Supply. The project received approximately €1 billion in public funding, approved under the Important Project of Common European Interest on Microelectronics and Communication Technologies, IPCEI-MECT framework. This 20% subsidy rate is lower than what is typically seen in the US or Asia, but it was sufficient to anchor the investment in Germany against competing offers. An audit of the construction timeline reveals a project moving with remarkable adherence to schedule, a rarity in large-scale European infrastructure. Ground was broken in May 2023. By late 2024, the building shell was complete, and the topping out ceremony was held. Throughout 2025, the facility has been in the hookup phase. This involves the installation of the tools, the lithography steppers, etchers, and deposition machines. This is the most expensive phase of any fab project. The fab is scheduled to begin commercial production in fall 2026. When fully operational, it will create 1,000 highly skilled direct jobs and support an estimated 6,000 indirect jobs in the region. The Dresden fab produces 300mm wafers focused on analog, mixed signal, and power semiconductors. While the public conversation about AI focuses on GPUs made by NVIDIA/TSMC, these chips consume voracious amounts of electricity. The power delivery networks that step down high-voltage grid power to the sub-1 volt levels needed by a GPU require ultra-efficient power stages. Infineon's chips are the muscle that allows the brain of AI to function. Without efficient power semiconductors, data centers would overheat or require impossible amounts of energy. Dresden's output is thus a critical enabler of the European AI infrastructure. As German automakers transition to software-defined vehicles, SDVs, the chip content per car is skyrocketing from $500 to over $1,500. By locating the production of these chips in Dresden, mere hours from the assembly lines of Wolfsburg and Leipzig, Germany creates a just-in-time silicon supply chain, insulating its GDP-critical auto sector from Asian logistics bottlenecks. Vishay, Itzehoe, Germany. While Infineon grabs headlines, Vishay's expansion in Itzehoe represents the critical mid-market layer of the supply chain. Vishay is expanding its existing site to add a 300mm wafer fabrication line, a project valued at approximately $400 million, €372 million. Groundbreaking occurred in March 2023. The structural topping out was achieved in August 2024. The facility is in the final stages of qualification. The clean room, a massive vibration-isolated manufacturing floor, has been certified, and pilot wafers are running through the line. Commercial deliveries are expected to ramp up through 2026. Interestingly, Vishay opted to proceed without direct reliance on the slow-moving EU CHIPS Act funding streams for the initial phase, driven by the urgency of customer demand. "We are not cutting edge, we're just not fancy enough," noted local management, highlighting how the EU's funding mechanisms often overlook essential mature nodes in favor of flashy advanced nodes. The Itzehoe expansion is part of a brutal but necessary restructuring known as Vishay 3.0. Moving from 200mm to 300mm wafers, more than doubles the surface area, allowing 2.25x as many chips to be printed per batch. This economy of scale is essential for competing with Chinese manufacturers who are aggressively flooding the market with legacy power chips. To fund and feed this new efficient site, Vishay has closed older, smaller plants in Fichtelberg, Germany, Milwaukee, USA, and Shanghai, China throughout 2025 and 2026. This centralization strategy sacrifices geographic diversity for operational efficiency, creating a campus model in Itzehoe that is robust against local economic fluctuations, but creates a single point of failure. Silicon Box, Novara, Italy. For decades, packaging, the process of putting a silicon chip into a protective plastic casing, was considered low-value work, mostly outsourced to Southeast Asia. However, the slowing of Moore's law has changed this. We can no longer easily make chips smaller, so we are making them smarter by stitching multiple chips together, chiplets, side by side, or stacking them vertically. This advanced packaging is now as high-tech as the chip making itself. Europe has historically had near-zero capacity in this domain. If a chip was made in Dresden, it still had to fly to Malaysia or Taiwan to be packaged before it could be used in a German car. This was a gaping hole in European sovereignty. Silicon Box, a Singaporean unicorn founded by the creators of Marvell Technology, selected Novara, Piedmont, Italy, for its first major expansion outside Asia. The total investment is 3.2 billion euros. In December 2024, the European Commission approved 1.3 billion euros in Italian state aid for the project, verifying that it met the first-of-a-kind criteria necessary to bypass normal state aid rules. The plant will use panel-level packaging, PLP. Instead of working on round wafers, Silicon Box mounts chips on large rectangular panels, similar to solar panels. This allows for 6 to 8 times higher manufacturing efficiency than standard methods. Unlike the nearly complete German projects, the Italian project is in its infancy. Construction is scheduled to begin in the second half of 2025. Initial production is targeted for Q1 2028, with full capacity reached by 2033. The facility will create 1,600 highly skilled jobs. More importantly, it completes the European value chain. For the first time, a high-end processor could be designed in the UK, fabricated in Germany, and packaged in Italy, never leaving the European sphere of influence. Imec, Málaga, Spain. Spain's semiconductor ambitions were initially channeled through the PERTE chip program, a $12 billion fund. While industrial attraction proved difficult, see Broadcom below, Spain successfully courted Imec, the world's premier semiconductor research institute based in Belgium. A collaboration framework was signed in July 2024, followed by land allocation in Málaga Tech Park in early 2025. 615 million euros, primarily funded by the Spanish central government, 500 million euros, and the Andalusian regional government. The project is in the architectural and facility design phase. The first employees have been hired and are currently training at Imec's headquarters in Leuven, Belgium, preparing to transfer to Málaga once construction advances. The facility aims to be operational around 2030. Why Málaga? The choice was strategic, leveraging the region's existing strength in biomedicine, specifically the IBMA Institute. The Málaga fab will not just make smaller transistors, it will focus on beyond CMOS technologies, specifically the integration of biology and electronics. One of the core missions of this facility is to develop chips for photonics-based DNA sequencing. By using silicon manufacturing techniques to build microscopic fluid channels and sensors, Imec aims to reduce the cost of sequencing a human genome to $10. This would revolutionize personalized medicine. This investment acknowledges that Spain cannot compete with Germany on volume manufacturing. Instead, it positions Spain as the leader in the next wave of computing, where biology and silicon merge. Broadcom, Spain. In 2023, Broadcom announced plans to build a $1 billion back-end facility in Spain, hailed by the Spanish government as a triumph of the PERTE chip strategy. By July 2025, the project was officially dead. The failure of the Broadcom project is a multifaceted cautionary tale. Reports indicate that the shifting political landscape in the US, the Trump effect, and America First policies played a decisive role. As the US government considers new tariffs and incentives to keep manufacturing domestic, the political risk of opening a major new facility in Europe increased for US executives. The Spanish government's requirement for staggered subsidy payments clashed with Broadcom's demand for upfront capital to cover equipment procurement. Unlike Dresden, which has a 30-year history of chip-making, Spain lacks a dense network of equipment suppliers and maintenance engineers. Broadcom realized that operating a lone outpost in Spain would be logistically difficult and expensive compared to expanding in an existing hub. The Broadcom cancellation cements the reality of a two-speed Europe. Northern Europe, Germany, UK, retains the industrial core, attracting manufacturing FDI. Southern Europe is largely relegated to R&D, Imec, or must rely on massive state intervention to create greenfield capabilities, Silicon Box, Italy. The vision of a distributed, equal semiconductor landscape across the continent has largely failed. An audit of the European semiconductor landscape in 2026 reveals a massive, uncomfortable truth. Despite nearly $100 billion in mobilized intent, Europe has not solved its most critical dependency. None of the investments detailed address the production of leading-edge logic, 5 nanometer, 3 nanometer, 2 nanometer. These are the chips that run iPhones, train ChatGPT, and guide autonomous missiles. For these, Europe remains 100% dependent on TSMC in Taiwan and Samsung in Korea. The Intel Magdeburg project, which was supposed to solve this, has faced repeated delays and skepticism, leaving a hole in the heart of the CHIPS Act. GlobalWafers, Italy. In the fertile plains of Piedmont, northern Italy, a transformation is taking place that symbolizes the shift from legacy production to the technological frontier. GlobalWafers, the world's third-largest supplier of silicon wafers, has operated in Italy for decades through its subsidiary MEMS Electronic Materials S.p.A. For nearly 50 years, the site in Novara has produced silicon, but the recent inauguration of the Fab 300 facility marks a definitive break with the past. The Fab 300 project is a €450 million investment dedicated to the manufacturing of 300mm or 12-inch silicon wafers. To the layperson, the difference between the older standard of 200mm wafers and the modern 300mm wafer might seem like a mere change in geometry. In the semiconductor industry, it is a change in era. The 300mm wafer is the standard platform for all advanced logic, the brains of computers and smartphones, and high-density memory. By establishing a fully integrated 300mm manufacturing line in Italy, GlobalWafers is plugging a gaping hole in the European ecosystem. Previously, European fabs often had to import these advanced substrates from Asia. Fab 300 localizes this critical input. One of the most significant aspects of the GlobalWafers investment is the concept of vertical integration within a localized geography. A silicon wafer does not begin as a disk, it begins as a crystal. The process involves melting hyper-pure silicon in a crucible and slowly drawing out a single perfect cylindrical crystal, an ingot, using a seed crystal. This process, known as Cholesky growth, is a dark art of physics and thermal management. GlobalWafers operates crystal growth facilities in Merano, Italy. The new Fab 300 in Novara complements this by providing the downstream polishing and epitaxy capabilities. Epitaxy involves growing a perfect layer of crystal on top of the polished wafer, a necessary step for high-performance chips. By integrating the crystal growth in Merano with the processing in Novara, GlobalWafers has created what it describes as one of Europe's few fully integrated 300mm wafer value chains. This means the entire life cycle of the raw material, from the solidification of the ingot to the final inspection of the polished wafer, occurs within Italian borders. This reduces logistics costs, minimizes the carbon footprint associated with transport, and insulates the supply chain from disruptions in global shipping. The Fab 300 project is a prime example of the European Chips Act in action. The facility received 103 million euros in funding through the IPCEI on microelectronics and communication technologies, IPCEI ME/CT. This grant, covering nearly a quarter of the total investment, was crucial in de-risking the decision to expand in a high-cost region like Europe rather than in lower-cost Asian jurisdictions. The inauguration of the facility was also a moment of silicon diplomacy. Attended by Doris Hu, the chairperson of GlobalWafers, alongside high-ranking Italian officials like Adolfo Urso, the Minister of Enterprises and Made in Italy, and Vincent Tsai, Taiwan's representative to Italy, the event underscored the deepening economic ties between Taiwan and Europe. In an industry often dominated by geopolitical friction, the collaboration between a Taiwanese titan and the Italian state serves as a model of cross-border cooperation. Doris Hu explicitly framed the factory not just as a manufacturing site, but as a symbol of innovation, sustainability, and shared growth, highlighting how the technical expertise of the Italian team has become a pillar of GlobalWafers' global strategy. The modern semiconductor supply chain is scrutinized not just for its output, but for its inputs, specifically energy and water. Fab 300 has been engineered to meet the RE100 standard, a global corporate renewable energy initiative. The facility targets the use of 100% renewable energy and has implemented systems to recycle approximately 50% of its water. In the water-stressed context of Southern Europe, this focus on hydrology is not merely greenwashing, but an operational necessity to ensure the plant's long-term viability. By integrating these sustainability metrics into the core design of the fab, GlobalWafers is positioning its Italian wafers as a premium, low-carbon product, attractive to European car makers and device manufacturers who must now account for the embedded carbon in their supply chains. Soitec, France. Located in the technological cluster of Bernal, near Grenoble, Soitec is the pioneer of engineered substrates. As Moore's law, the observation that computing power doubles every 2 years, slows down due to the physical limits of silicon, the industry has turned to more than more innovation. This approach focuses not just on shrinking transistors, but on changing the material they are built on to achieve better performance, lower power consumption, and higher connectivity. Soitec's flagship technology, Silicon on Insulator, SOI, involves placing a thin layer of insulating material, usually silicon oxide, between the silicon wafer base and the top layer where the transistors sit. This insulation prevents the leakage of electricity, a major problem in standard silicon chips, thereby drastically improving energy efficiency. This technology has become the global standard for the radio frequency chips found in every smartphone, enabling 4G and 5G connectivity. The centerpiece of Soitec's recent investment strategy is the Bernin 4 fabrication facility. This expansion, representing a total investment of approximately 400 million euros, marks a strategic pivot from consumer electronics toward the automotive sector. The European automotive industry is currently undergoing a traumatic but necessary transition from internal combustion engines to electric propulsion. In this new world, the currency of competition is range and charging speed. Both are determined by the efficiency of the power electronics that convert energy from the battery to the motor. Silicon, the workhorse of the chip industry, struggles with the high voltages and temperatures inside an electric vehicle's powertrain. The solution is silicon carbide, a compound material that is essentially a diamond-like lattice of silicon and carbon. SiC chips can handle higher voltages with far less energy loss than silicon. However, growing SiC crystals is notoriously difficult, slow, and expensive, making SiC wafers cost-prohibitive for many mass-market vehicles. This is where Soitec's Smart SiC technology comes into play, creating the rationale for the Bernin 4 factory. Utilizing its proprietary Smart Cut process, effectively an atomic scalpel, Soitec can take a single, expensive, high-quality SiC donor wafer and slice off a microscopically thin layer. This thin layer is then bonded to a cheaper, highly conductive carrier wafer, often made of polycrystalline SiC. The genius of this approach is resource efficiency. Because only a tiny sliver of the expensive monocrystalline SiC is used for the active layer, the original donor wafer can be repolished and reused 10 times or more. This dramatically lowers the cost of the final wafer and significantly reduces the carbon footprint of production. Soitec claims that its Smart SiC wafers can reduce the CO2 emissions associated with wafer production by 75% compared to traditional bulk SiC wafers. The Bernin 4 facility is designed to ramp up the production of these Smart SiC wafers to 500,000 units per year by 2030. This volume is intended to feed the hunger of European chip makers like STMicroelectronics and Infineon, who in turn supply the inverters for Volkswagen, Stellantis, and Renault. Thus, the expansion in Bernin is a direct infrastructure investment in the viability of the European electric vehicle industry. Soitec's success is inseparable from its location. Grenoble is often referred to as the Silicon Valley of the Alps due to its dense concentration of research and industry. The Smart SiC technology was not developed in isolation, but emerged from the Substrate Innovation Center located at CEA Leyte, a world-renowned government-funded research institute. This lab-to-fab model is a distinct feature of the European semiconductor strategy. By co-locating the industrial production, Bernin 4, with the fundamental research, CEA Leyte, Europe accelerates the transfer of technology. The IPCEI funding that supports Soitec, often cited in the range of hundreds of millions of euros across various projects, specifically targets this gap between the laboratory proof of concept and the high-volume industrial ramp-up. The Bernin 4 project is expected to create 400 direct, highly skilled jobs, further reinforcing the specialized talent pool of the Isère region. Merck KGaA, Germany. If the wafer is the canvas, the chemicals are the paint and the brushes. The manufacturing of a single microchip involves hundreds of process steps, each requiring specific liquid chemistries for cleaning, etching, planarization, polishing, and deposition. A defect in the chemical purity at the parts per trillion level can render a chip useless. In this domain, the German science and technology giant Merck KGaA, operating as EMD Electronics in North America, is a global hegemon. Recognizing the semiconductor industry's supercycle, driven by artificial intelligence, the Internet of Things, and big data, Merck launched an ambitious growth program named Level Up in late 2021. The program commits the company to investing significantly more than 3 billion euros in innovation and capacity expansion by 2025. This is not merely the maintenance of the status quo, it is an aggressive push to become the premier molecular architect of the digital age. While Merck is a global company with a footprint in Asia and the Americas, its heart remains in Darmstadt, Germany. A critical pillar of the Level Up program is the expansion of the Darmstadt campus into a global center for electronic materials research. The company has invested in a dedicated electronics technology center at its headquarters. This facility serves a vital strategic function. It bridges the gap between basic chemical research and the specific needs of chip makers. In the semiconductor world, process integration is key. A new molecule might theoretically be a better insulator, but if it doesn't adhere to copper wiring or reacts poorly with a photoresist, it is useless. The Darmstadt Center allows Merck to test its materials in an environment that mimics a customer's fab, accelerating the development cycle. Additionally, Merck is investing 62 million euros in a new quality control facility in Darmstadt, leveraging its expertise from the life sciences sector, where purity is a matter of life and death, to ensure the reliability of its electronic materials. Merck identifies its big three growth engines within the electronics sector as semiconductor solutions, delivery systems and services, DSS, and display solutions. The Level Up program is heavily skewed towards semiconductor solutions. Interestingly, one of the largest single investments under this program is not in Europe, but in Taiwan. Merck recently inaugurated a mega site in Kaohsiung, representing an investment of 500 million euros. While this facility is in Asia, its strategic logic is deeply relevant to Europe. It demonstrates that for a European materials company to lead, it must be embedded in the world's most advanced manufacturing ecosystem, TSMC in Taiwan. The knowledge, scale, and technical insights gained in Kaohsiung flow back to the European R&D hubs, strengthening the overall competence of the company. Simultaneously, Merck is expanding its presence in the United States with a 300 million euro investment in hometown Pennsylvania to create the world's largest integrated specialty gases facility. This creates a triad of major hubs, Germany, Taiwan, USA, that provides Merck with a resilient follow-the-sun capability. If a supply shock hits one region, the others can potentially compensate, securing the supply for European customers who rely on Merck's global network for specialized precursors. Merck's dominance is also the result of strategic consolidation. The acquisitions of Versum Materials and Intermolecular in recent years have given Merck one of the broadest portfolios in the industry. They can supply the spin-on dielectric materials that insulate the transistors, the organometallic precursors used to deposit atomic layers of metal, and the chemical-mechanical planarization slurries used to polish the wafer flat. Under the Level Up program, these disparate portfolios are being integrated into comprehensive solutions. For a European fab manager, dealing with a single supplier who understands the chemical interaction between the slurry and the dielectric offers a significant efficiency advantage, further embedding Merck into the continent's manufacturing fabric. Air Liquide. In the rarefied environment of a clean room, the air we breathe is a contaminant. Chip manufacturing takes place in atmospheres of precisely controlled gases. Nitrogen is the workhorse, used to purge equipment and prevent oxidation. Hydrogen is used as a carrier gas and to anneal or heat treat the silicon to repair crystal damage. Oxygen is used to grow oxide layers. Rare gases like argon, helium, krypton, and xenon are essential for the plasma processes that etch circuits and the lasers that print them. The supply of these gases is the invisible infrastructure of the industry. Air Liquide has placed a massive strategic bet on Dresden, Germany, the capital of the Silicon Saxony cluster. The company recently announced an investment of over 250 million euros to construct state-of-the-art gas production facilities in the region. This is the largest single investment Air Liquide has ever made for the electronics industry in Europe. The project involves the construction of 3 separate air separation units, or ASUs, and 2 hydrogen production units. This scale is telling. It suggests a massive increase in local consumption. While Air Liquide often protects the identity of its specific customers, the timing and location point directly to the new European Semiconductor Manufacturing Company, or ESMC, joint venture, which brings TSMC to Dresden, as well as expansions by existing players like GlobalFoundries, Bosch, and Infineon. By building this infrastructure, Air Liquide is effectively acting as a utility provider for the cluster. The gases will likely be distributed via a pipeline network, a highly efficient method that eliminates the need for thousands of truck deliveries. This creates a lock-in effect that strengthens the cluster. Once the pipeline infrastructure is in place, it becomes much more attractive for other semiconductor companies to locate nearby, creating a virtuous cycle of industrial density. Air Liquide emphasizes that these new plants will be next-generation facilities, heavily digitized for predictive maintenance. In chip manufacturing, a gas interruption of even a few seconds can scrap millions of euros worth of wafers. Therefore, the reliability provided by these new automated plants is as much a part of the product as the gas itself. Linde, the other titan of the industry, formed from the merger of the German Linde AG and the American Praxair, has a deep footprint in Europe. One of its most significant recent contributions to the European ecosystem is the pioneering of green hydrogen for chip making. At Infineon's production site in Villach, Austria, Linde constructed and operates a 2-megawatt electrolyzer plant. Historically, the hydrogen used in fabs was gray, produced from natural gas via steam methane reforming, a process that emits CO2. The new Villach plant utilizes proton exchange membrane technology to split water into hydrogen and oxygen using renewable electricity. This project is a critical proof of concept for the entire industry. It demonstrates that green hydrogen can be produced reliably and, crucially, can be purified to the 9 nines, or 99.999999% purity level required for semiconductor manufacturing. For Infineon, this allows for a reduction in the carbon footprint of their chips, a key selling point. Linde is taking the lessons from this pilot and applying them across its global network. Both Linde and Air Liquide utilize their global operations to secure Europe's supply of rare gases. The war in Ukraine exposed a critical vulnerability, as Ukraine was a major supplier of neon used in lithography lasers, and Russia was a source of other rare gases. In response, these companies have invested in expanding rare gas sourcing capabilities in politically stable regions and developing recycling technologies. Linde, for instance, has invested heavily in rare gas production in the US, building a new air separation unit in Texas to support the space sector, which also uses rare gases, creating cross-industry synergies. This global diversification ensures that European fabs are buffered against future geopolitical shocks affecting these niche but vital materials. Shin-Etsu Chemical. In the hierarchy of semiconductor materials, Shin-Etsu Chemical occupies a throne of undisputed authority. It is the world's largest supplier of silicon wafers, the the thin, polished discs of single crystal silicon that serve as the canvas for every integrated circuit. Alongside its domestic rival Sumco, Shin-Etsu controls the majority of the global wafer market, a duopoly that grants Japan immense leverage over the global electronics industry. But Shin-Etsu is more than just a wafer maker. It is a chemical conglomerate with dominant positions in photoresists, photomask blanks, and encapsulation materials. For much of its history, Shin-Etsu's strategy was defined by centralization. Its massive Naoetsu plant in Niigata Prefecture was the beating heart of its operations, exporting materials to the world. However, the lessons of the 2011 Tohoku earthquake and subsequent geopolitical frictions have forced a strategic pivot. Shin-Etsu has adopted a dual-base philosophy, the imperative to manufacture critical materials in at least 2 geographically distinct locations to ensure business continuity for its customers. This philosophy is the driving force behind its European expansion. European customers, particularly in the automotive sector, demand just-in-time delivery and absolute assurance that a typhoon in Japan will not stop the production of cars in Stuttgart. Shin-Etsu is responding by transforming its European outposts from sales offices into robust manufacturing hubs. While recent headlines focus on the EU, Shin-Etsu's commitment to the European region is anchored in a deep history in the United Kingdom. Shin-Etsu Hondo Tai Europe, SEH Europe, located in Livingston, Scotland, is a testament to the company's long-term vision. Established in the 1980s during the boom of Silicon Glen, when Scotland was envisioned as the manufacturing hub of Europe, SEH Europe has survived the exodus of other electronics manufacturers to become a critical node in the continent's supply chain. The Livingston facility is not a relic, it is a highly specialized manufacturing site. It produces 150mm and 200mm polished and epitaxial wafers. To the layperson, these smaller wafer sizes, compared to the leading-edge 300mm wafers used in smartphones, might seem outdated. In reality, they are the gold standard for power semiconductors, the chips that manage electricity in electric vehicles, wind turbines, and industrial robots. As Europe aggressively pursues its Green Deal and the electrification of its economy, the demand for these specific wafers has skyrocketed. SEH Europe performs the entire value-add process: crystal growing, pulling a silicon ingot from molten rock, slicing, polishing, and epitaxy, growing a pure crystalline layer on top of the wafer. This facility serves as the logistical and manufacturing hub for the entire EMEA region, supported by sales offices in Munich and Nice that maintain close contact with continental customers. The plant's continued operation and relevance highlight Shin-Etsu's ability to adapt its legacy assets to meet modern demands, ensuring that the European automotive industry has a local source for its most fundamental raw material. Shin-Etsu's engagement with Europe extends beyond silicon. In 2025, the company announced a significant investment of 10 billion yen, approximately 65 million euros, to strengthen its pharmaceutical cellulose business. A major portion of this investment is directed at its subsidiary, SE Tylose GmbH & Co. KG in Wiesbaden, Germany. While this investment targets pharmaceutical excipients, specifically LHPC, used in tablet binding, it is structurally significant for the semiconductor discussion. It demonstrates Shin-Etsu's willingness to make heavy capital investments in Germany, building the dual base infrastructure that mirrors its Japanese capabilities. The logic applied here, duplicating Japanese production lines in Europe to secure supply chains, is directly applicable to its electronic materials portfolio. As the European Chips Act gains momentum, Industry observers expect Shin-Etsu to leverage this existing German infrastructure and legal entity to potentially localize the production of semiconductor-grade chemicals, further embedding itself into the German industrial ecosystem alongside customers like Infineon and Bosch. Resonac Corporation. In January 2023, the landscape of the global chemical industry shifted with the birth of Resonac Corporation. Formed through the merger of two historic Japanese firms, Showa Denko and Showa Denko Materials, formerly Hitachi Chemical, Resonac was created with a singular purpose: to become a co-creative chemical company capable of solving the complex material challenges of the digital age. The merger combined Showa Denko's expertise in upstream petrochemicals and gases with Hitachi Chemical's mastery of downstream functional materials. The result is a vertically integrated giant with roughly 450 billion yen in semiconductor and electronic materials sales, holding top market shares in critical niches like polishing slurries, copper-clad laminates, and packaging materials. Resonac's strategy is predicated on a fundamental shift in the semiconductor industry. For decades, progress was defined by Moore's Law, the shrinking of transistors on a chip. This front-end innovation is reaching physical limits. The new frontier is back-end innovation, advanced packaging. This involves stacking chips vertically, 3D integration, or stitching different chips together, chiplets, to boost performance. Resonac is the global leader in the materials required for this packaging revolution. Its die-bonding films, mold compounds, and photosensitive dielectrics are the glues and insulators that hold these complex 3D structures together. Recognizing that Europe is a hotbed for automotive and industrial innovation, Resonac has established Resonac Europe GmbH in Munich, Germany as its regional headquarters. Munich is a strategic choice, placing Resonac in the physical center of Europe's industrial powerhouse, Bavaria. It sits within driving distance of key customers like Infineon, Siemens, and the R&D centers of BMW and Audi. The Munich office is more than a sales outpost. It is a center for co-creation. Resonac acknowledges that modern material problems are too complex to solve in isolation. In Japan, it leads the Joint 2 and Joint 3 consortia, bringing together competitors and customers to develop packaging standards. In Europe, Resonac applies this same philosophy. The European team works directly with local chip makers and automotive Tier 1 suppliers to qualify new materials for next-generation power modules. Europe's aggressive transition to EVs is a primary driver for Resonac's European business. EVs require power modules that can withstand immense heat and vibration. Resonac provides the silicon carbide epitaxial wafers and the heat-dissipating packaging materials that make these modules possible. The company is actively integrating its materials into the European automotive supply chain. For example, its materials are being tested for use in power module integration, a process where the chip and the package are designed simultaneously to optimize thermal performance. By having a robust team in Munich, Resonac can iterate these designs with German engineers in real time, bypassing the time zone and cultural barriers that would exist if everything were run out of Tokyo. Under the leadership of Hidehito Takahashi, Resonac has adopted an aggressive posture toward expansion. Takahashi has publicly stated his intention to pursue strategic acquisitions to scale up the company's capabilities, specifically eyeing opportunities that might arise from the restructuring of the Japanese materials sector, such as the privatization of JSR. Simultaneously, Resonac is streamlining its portfolio to focus on high-growth semiconductor areas. In July 2025, the company completed the sale of its UK subsidiary, F2 Chemicals, to R Capital Partners. While F2 Chemicals was a solid business, its focus on fluorinated compounds was deemed non-core to the semiconductor packaging strategy. This divestment frees up capital and management attention, allowing Resonac to double down on its investments in the Silicon Saxony cluster and its Munich R&D hub. This strategic clarity signals to the market that Resonac is fully committed to becoming the premier partner for Europe's advanced chip packaging needs. JSR Corporation. If Shin-Etsu is the king of wafers and Resonac the master of packaging, JSR Corporation is the vanguard of lithography. JSR dominates the global market for photoresists, the light-sensitive liquids that are coated onto wafers and exposed to light to create circuit patterns. Without JSR's chemistry, the advanced lithography machines made by ASML would be effectively useless. JSR has recently been the subject of a massive geopolitical maneuver. In a deal valued at approximately $6.3 billion, the company was acquired by the Japan Investment Corporation, JIC, a state-backed sovereign wealth fund. This privatization is a deliberate strategy to shield JSR from the short-term pressures of the stock market. Developing new photoresists for future technology nodes, like 2nm or 1.4nm, requires massive R&D spending with uncertain timelines. By going private under government wing, JSR can invest aggressively in long-term technologies without worrying about quarterly dividends. This move also underscores the Japanese government's view of JSR's technology as a matter of national security. JSR's European strategy is inextricably linked to Belgium. Its subsidiary, JSR Micro NV, is based in Leuven, a small city with a colossal reputation in the semiconductor world. Leuven is home to Imec, Inter-University Microelectronics Center, widely considered the world's most advanced semiconductor research organization. Imec is the Switzerland of the chip wars, a neutral ground where TSMC, Intel, Samsung, and ASML collaborate to define the roadmap for the next decade of computing. By locating its European headquarters and manufacturing site in Leuven, JSR Micro NV has physically embedded itself into this innovation engine. The relationship is symbiotic. Imec operates advanced pilot lines that simulate the manufacturing processes of the future. To run these lines, they need next-generation photoresists that don't exist yet as commercial products. JSR provides these experimental materials. In return, JSR gets early data on how its chemicals perform on the world's most advanced tools, including ASML's high-NA UEV scanners. This feedback loop allows JSR to perfect its products years before its competitors, maintaining its best front-end supplier status with major European customers like STMicroelectronics. JSR Micro NV is not just a lab, it is a high-volume manufacturing site. The company has continuously invested in expanding this facility to meet European demand. Recent expansions include new warehouse capacity, advanced quality control labs, and significant environmental infrastructure. Environmental sustainability is a critical driver for JSR in Europe. The EU is leading the world in regulating PFAS, a class of chemicals often used in photoresists for their stability. However, impending bans on PFAS threaten the entire semiconductor industry. JSR is using its Belgium hub to pioneer PFAS-free photoresists and filtration technologies. The company recently broke ground on a new wastewater treatment plant at its Leuven site, designed to ensure that its manufacturing processes meet the strictest EU environmental standards. By doing this difficult R&D and compliance work in Europe, JSR provides a regulatory shield for its customers, ensuring that their supply of critical materials remains compliant with European law. The privatization by JIC is expected to further accelerate JSR's European activities. Free from the need to justify every expense to public shareholders, JSR can double down on its collaboration with Imec and potentially acquire smaller European material firms to round out its portfolio, further cementing its role as the chemical backbone of European lithography. Fujifilm Electronic Materials. Fujifilm, a brand once synonymous with photographic film, has executed one of the most successful corporate pivots in history. Today, it is a diversified technology giant, and its electronic materials division is a powerhouse in the semiconductor supply chain. Unlike competitors who specialize in one or two niches, Fujifilm's strategy is to be a one-stop solution, providing a comprehensive suite of chemicals ranging from photoresists and developers to cleaners and CMP slurries. Fujifilm is putting its money where its mouth is with one of the most significant tangible investments in European material production. In early 2025, the company confirmed a capital investment of 25 million euros, approximately 4 billion yen, to expand its production site in Zwijndrecht, Belgium, near the port of Antwerp. This investment follows a previous 30 million euro expansion announced in 2023, bringing the total recent capital injection into the site to over 55 million euros. This sustained investment campaign is transforming the Zwijndrecht facility into a mega hub for semiconductor chemicals. The expansion includes the construction of 4,000 square meters of new space, housing state-of-the-art cleanroom R&D labs, advanced quality control centers, and multi-purpose production lines. The project is supported by Flanders Investment and Trade, FIT, highlighting the close cooperation between the Japanese corporate sector and the Belgian regional government. The specific focus of the new investment is telling. It is targeted at increasing production capacity for CMP slurries and photolithography developers. CMP, chemical mechanical polishing, is a process that has become critical as chips have moved from 2D to 3D structures. In modern chip making, wafers are built up in layers: insulators, copper wiring, transistors. After each layer is deposited, the wafer surface becomes uneven. CMP uses a chemical slurry containing microscopic abrasives to polish the wafer perfectly flat before the next layer is added. As chips become more complex with more layers, the consumption of CMP slurry increases exponentially. The market for CMP slurries is growing at an annual rate of 13%, driven by advanced logic and memory chips. By localizing CMP slurry production in Belgium, Fujifilm is addressing a critical logistics challenge. CMP slurries are heavy, liquid-based products that are expensive to ship from Asia. They also have a limited shelf life. Producing them in Zwijndrecht allows Fujifilm to deliver them by road to customers in Germany, Infineon, GlobalFoundries, France, STMicroelectronics, and Ireland, Intel, within days. Fujifilm's European president, Hans Vlobergs, has articulated a clear strategy: local supply for local demand. The European semiconductor market is heavily skewed toward the automotive and industrial sectors, chips that go into cars, robots, and medical devices. These industries operate on just-in-time principles and demand absolute reliability. They cannot tolerate a supply chain that involves a 6-week ocean voyage from Japan. Fujifilm operates a network of 5 manufacturing plants across Europe, the main hub in Zwijndrecht, Belgium, specialized sites in Saint-Fromond and Saint-Chéron, France, a facility in Riddings, UK, and a site in Milan, Italy. This distributed footprint provides redundancy and proximity. The new investments in Belgium are scheduled to come online in spring 2026, perfectly timed to support the ramp-up of new fabs currently under construction across the continent. Taiyo Nippon Sanso, or Nippon gases. While solids and liquids form the structure of a chip, gases are the tools used to sculpt them. High-purity gases are used to etch patterns, deposit layers, and dope silicon to change its electrical properties. Taiyo Nippon Sanso, part of the Nippon Sanso Holdings Corporation, NSHD, is a dominant global player in this space. In Europe, it operates under the brand Nippon Gases, having solidified its position through the strategic acquisition of Praxair's European assets in 2018. The crown jewel of Nippon Gas's European electronics business is its dedicated semiconductor specialty gases production facility in Oeville, Belgium. This plant is a high-tech fortress designed to handle some of the most volatile and dangerous substances on Earth, gases like arsine, phosphine, and diborane, and purify them to levels where impurities are counted in parts per billion, ppb. The Oeville facility is a strategic asset for the European Union. Without a local source of these electronic-grade gases, European fabs would be entirely dependent on imports from the US or Asia. Given that these gases are hazardous and difficult to transport, reliance on long-distance shipping creates immense risk. Nippon Gas's local production ensures that European chipmakers have a secure, compliant, and reliable source of manufacturing breadth. Nippon Gases is not content simply delivering cylinders. It is moving up the value chain with its total gas management service. In this model, Nippon Gases embeds its own staff and infrastructure directly inside the customer's fab. They manage the entire gas supply ecosystem, from bulk storage tanks to the intricate piping that feeds the lithography tools 24 hours a day. This integration makes Nippon Gases a partner in the fab's operation, rather than just a vendor. Reacting to the booming demand and competitive pressure from rivals like Air Liquide, which announced a $250 million investment in 2025, Nippon Gases is continuously upgrading its European infrastructure. This includes investments in abatement systems, technology that scrubs the exhaust gases from fabs to remove harmful greenhouse gases before they are released. This focus on sustainability aligns perfectly with the EU's Green Deal and the carbon neutrality goals of customers like Apple and BMW, who buy the final chips. Nagase & Company. Nagase is a specialized trading house that acts as the bridge between Japanese material innovation and European industrial demand. It has aggressively expanded its European footprint, establishing a network of offices in Dusseldorf, London, and Lyon. Nagase's strategy goes beyond simple import-export. It operates innovation laboratories in Europe, such as its Life Science Lab in Lyon, to test and adapt Japanese materials for local applications. In the semiconductor space, Nagase identifies specific gaps in the European supply chain, perhaps a niche cleaning solvent or a specialized polymer, and sources the solution from its vast network of Japanese manufacturers. Its recent acquisition of the high-purity chemical business of US-based Sachem for $101 million significantly boosts its ability to supply critical process chemicals to the European market. Tokuyama. Tokuyama Corporation is a world leader in high-purity polychlorine silicon, the raw material from which silicon wafers are made. While its primary manufacturing base remains in Asia, including a new venture in Taiwan and facilities in Malaysia, Tokuyama plays a vital role in the European supply chain. Tokuyama supplies the raw silicon to European wafer manufacturers like Siltronic, Germany. Its recent strategic focus has been on improving the logistics and sales efficiency of its electronic materials division in Europe to capture the market recovery. By ensuring a stable flow of raw silicon into Europe, Tokuyama sits at the very beginning of the continent's chip supply chain. Topan, or Texend photomask. Photomasks are the quartz plates containing the circuit patterns that are projected onto wafers. They are the negatives of the chip photography process. Topan, operating as Texend Photomask, runs the Advanced Mask Technology Center, AMTC, in Dresden, a joint venture with GlobalFoundries. Topan is investing heavily to install multi-beam mask writers from IMS Nanofabrication. These machines are capable of writing the incredibly fine patterns required for the 12 nm chips ESMC will produce. This investment ensures that Europe has a local source for high-end masks, reducing dependency on mask shops in Asia. HORIBA, a leader in precision measurement and mass flow controllers, devices that control the flow of gases into process chambers, HORIBA has a dedicated office in Dresden. Its equipment is the nervous system of a fab, monitoring processes in real time. HORIBA is expanding its local support capabilities to ensure that when TSMC's tools come online, HORIBA engineers are there to calibrate them. Kokusai Electric. Operating as Kokusai Semiconductor Europe, this company manufactures the thermal processing furnaces used to deposit thin films and anneal wafers. It is a member of the Silicon Saxony Industry Association and is scaling its service infrastructure to support the installed base of furnaces in the region. Ebara. Ebara Precision Machinery Europe is a top supplier of vacuum pumps and CMP tools. A fab runs under vacuum. Without Ebara's pumps, the clean rooms would stop functioning. Ebara is expanding its overhaul centers and support teams in Dresden to service the thousands of pumps that will be installed in the new ESMC facility. The cost of sovereignty, talent, energy, and the OpEx gap. The decision to build a fab is a 20-year financial commitment. While the European Chips Act and national subsidies can effectively offset the initial construction premium, CapEx, they cannot subsidize the daily operational costs, OpEx, that accumulate over decades. The OpEx gap between Europe and its competitors is the fundamental challenge to the long-term economic viability of the region's reindustrialization. Data indicates that the 10-year total cost of ownership, TCO, for a semiconductor facility in Europe is approximately 30 to 40% higher than in Taiwan or Southeast Asia. This gap is not driven by a single factor, but by the compounding effects of construction fluidity, energy premiums, and labor structures. Semiconductor manufacturing is hyper-intensive in its electricity usage. A modern fab consumes as much power as a small city. In 2025, industrial electricity prices in Germany and Italy remain structurally higher than in the US or Asia. The US benefits from abundant shale gas, and Asia often benefits from state-subsidized grids or lower regulatory burdens. For a fab consuming 1 terawatt-hour per year, a price difference of just 0.05 euros per kilowatt-hour translates to 50 million euros in annual excess OpEx. Over a 10-year period, this amounts to €500 million in lost competitiveness, equivalent to the cost of several EUV lithography machines. This structural disadvantage forces European fabs to focus on high-margin products like automotive ICs, where the chip cost is a small fraction of the final vehicle price, as they simply cannot compete on pure cost per transistor with Asian memory or commodity logic foundries. Furthermore, the occurrence of negative electricity prices in Europe, while sounding beneficial, signals grid instability and a lack of storage flexibility, which requires fabs to invest in expensive stabilization equipment to ensure the 9 nines, or 99.9999999% of reliability required for wafer processing. The semiconductor industry operates on a 24/7, 365 basis. The capital depreciation of a $10 billion tool set means that stopping the line is economically ruinous. This operational requirement clashes with the European social model, creating specific frictions in France and Germany. France, the 35-hour workweek is not an absolute cap, but it sets a low threshold for overtime pay and compensatory rest. To run a 24/7 fab, French sites often require a 5-shift or 6-shift system to cover the 168-hour week while adhering to legal limits on individual working time. In contrast, US or Asian sites might operate with 3 or 4 shifts. This effectively increases the headcount requirement by 20 to 30% for the same output, inflating the fully loaded labor cost significantly. Germany. The Works Council, Betriebsrat, holds significant co-determination rights regarding shift schedules, overtime, and operational changes. Adjusting shift patterns to match fluctuating market demand, a standard rapid practice in Taiwan, requires lengthy negotiations in Germany. This reduces operational agility. However, the labor cost metric is nuanced. While the hourly rate and social charges in Europe are high, the turnover rate is significantly lower than in the US or Asia. In the US semiconductor hubs like Arizona, the workforce has become increasingly transient, driving up recruitment and training costs. In clusters like Dresden and Grenoble, engineers often stay with companies for decades. This high retention translates to greater yield stability, deep institutional memory, and IP security, hidden economic benefits that partially offset the higher raw payroll costs. The most immediate constraint on European expansion is not capital, but human resources. The industry faces a shortage of thousands of engineers. Europe produces fewer electrical engineering graduates relative to industry demand than Taiwan or South Korea. The salary gap. A senior process engineer in Dresden might earn a base salary of 70,000 to 90,000 euros. In the US hubs of Arizona or Texas, the same role can command $130,000 to $160,000. This massive arbitrage creates a brain drain, attracting top European talent to US fabs. European nations are attempting to plug this gap with immigration. Poland relies on talent from Eastern Europe. Germany has simplified visa rules for Indian and Southeast Asian technical workers. However, physical constraints like housing shortages in Dresden, Grenoble, and Eindhoven act as a hard cap on how many immigrants can be absorbed into the clusters, threatening to stall the ramp-up of new facilities. Policy anatomy, from CHIPS Act 1.0 to 2.0. In 2025, the European Court of Auditors, ECA, delivered a scathing verdict on the original CHIPS Act. The auditors declared the goal of reaching 20% of the global market share by 2030 to be unrealistic and far off pace. The critique was not just about the numbers, but about the structure of the policy. The ECA report highlighted that much of the advertised 43 billion euros was mobilized rather than budgeted. Mobilized funds rely on private sector matching and member state contributions that may or may not materialize. In the case of Intel and Wolfspeed, the private matching funds evaporated, and thus the mobilized public money vanished with them. Furthermore, the governance structure, specifically the IPCEI mechanism, was criticized as labyrinthine and slow. By the time the complex state aid approvals were granted for projects like Crolles, the market cycle had often already shifted, leaving companies with approved subsidies for factories they no longer wanted to build immediately. In response to these failures, a CHIPS Act coalition comprising all 27 member states and major industry players has outlined the requirements for a CHIPS Act 2.0. The language of this new proposal reflects the lessons learned from the collapse of Phase 1. First, the fixation on market share percentage is being replaced by the concept of indispensability. The goal is no longer to be big, but to be essential. Europe aims to hold critical cards like ASML's lithography, STMicro's power chips, or Silicon Box's packaging that the rest of the world cannot function without. Second, the industry is demanding a secured budget line in the next EU multi-annual financial framework. They want real federalized European money, not just a patchwork of national promises that disappear when a country's budget court rules against them, as happened in Germany. Third, there is a push for fast-track permitting. The industry is calling for a guarantee that strategic projects will be approved in under 7 months, attempting to match the speed of US and Asian rivals. Finally, the new strategy emphasizes a demand-side focus. There is a recognition that building fabs without customers is futile. CHIPS Act 2.0 proposes semiconductor alliances that would formally link chipmakers with downstream industries, automotive, healthcare, and AI, to facilitate long-term offtake agreements, ensuring that if a factory is built, its capacity is pre-sold.